Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Hello there, ladies and gentlemen. Welcome back to the Ephemeris podcast. I'm your host, Aphelion, and thank you for joining me again this week for another episode in season 3 where we are covering news in astronomy. I apologize if my microphone is a little bit quiet today as my computer is making a lot of noise and that would be an issue to all of you listeners. So, anyways, that's besides the point. Let's talk about the 3 stories we're going to be covering today. So, the first one is going to be about how a multi lens telescope is changing observational astronomy, or might change observational astronomy for that matter. The second article is going to be us revisiting AI and how it's helping us with distant quasars. The third article we'll be talking about is galaxies in the universe and what James Webb Space Telescope has found out about these early galaxies. So, let's start off with our first story here. It's a nice segue from last week's article where we talked about optical interferometry and how you can use quantum memory to improve optical interferometry. We won't be getting back into the quantum stuff again, but we still have some exciting news here, and the article opens up the story as follows. Astronomers at Macquarie University have pioneered a new technique for observing celestial objects during the day, potentially allowing around-the-clock visual monitoring of satellites and greatly improving safety on Earth and in space. Your first question hopefully will be how. But let's get into that question as we describe the equipment we're working with, because it's quite fascinating. The first and most important thing that's used for this technology is the Huntsman telescope at Macquarie University. Hopefully I'm saying that correctly. I don't actually know. It's spelled in a bit of a peculiar way, so I can't figure it out as easily. But anyways, this Huntsman telescope that we have here, it's got 10 simultaneously functioning camera lenses in an array. And I'm assuming these are like regular use optical cameras type of lenses. I'm not sure exactly. These lenses are combined with focusing equipment for astronomy as well as an astronomy camera, one that's, designed for astronomy. And with this hardware, astronomers tried special broadband filters to block most of the daylight received during the observation. So that would leave us with light coming from celestial objects in the sky, obviously. I'm not aware of whether you can actually apply broadband filters to like smaller telescopes. If you can, that's all fine and dandy. This is a much bigger telescope that we're talking about. But if you can't, that makes this even more surprising news. So that is the backstory behind the technology and how astronomers were able to pull this off. And, it sounds really simple saying it, but configuring huge telescopes to filter out daylight surely can't be that easy. The amazing part about a breakthrough like this is how long astronomers have been trying to develop this technology and the ability to observe during the daytime. One of the authors on the story mentions that people have tried observing stars and satellites in optical wavelengths during the day for centuries, but it has been very difficult to do. So, yeah, that's all great. But how does this help us? Because, we can always, rely on doing observational astronomy in the night. What's so special about doing it during the day, and why does that make a difference? Well, there's a very simple answer to this, and it's that observing during the daytime allows us on the ground to observe objects that are close to the sun. Sort of objects that won't really make sense at nighttime on the ground. With space telescopes being around, obviously, there's kind of a workaround to that problem, but now that we have this technology, we are actually able to get observational data of things that are close to the sun on the ground. And yeah, also a thing about space telescopes is the availability and accessibility, not, because so many people are doing so many different studies trying to use space telescope data, perhaps being able to do certain things on the ground will sort of free up, or sort of like resolve that issue a little bit. That's my hypothesis. So that's the significance there. Some objects that you can sort of mention that belong in this category are like stars like Betelgeuse. They've had, or the Betelgeuse itself has had dimming in like the last few years, and if we're able to get the information for Betelgeuse on the ground with daylight observation, that might have made things easier. Who knows? And now that we're able to do that, we can continue collecting data in an easier manner for stars like Betelgeuse that are close to the sun. And yeah, daytime astronomy might become mainstream with this technology. So that is some nice news that I have for you, firstly. Secondly, it's a follow-up to a previous article. As I talked about in the beginning, it's about AI. So 2 episodes ago, I discussed an article about how AI is helping astrophysicists and nuclear physicists map out nuclides created through photosynthesis, but now we have found a new way in which AI can help the field of astronomy and astrophysics, and that is through neural networks that are developed by machine learning. They're helping us decode spectral data obtained by the Sloan Digital Sky Survey from quasars. We've talked about the Sloan Digital Sky Survey at some point, I think in season 1. Yeah, I think it was season 1 we talked about the Sloan Digital Sky Survey. It's helped us map out a lot of the universe, and it provides us with things like, spectral data from quasars. And there are some very complicated parts about this spectral data that we will talk about in just a moment, where AI can really chip in and help us sort of decipher all that data. Just to mention some numbers here, it has helped us find 107 rare neutral carbon absorbers that will tell us more about chemical compositions and stellar evolution from the early universe. Okay, now let's get into what all of this means. Let's start off with the neutral carbon absorbers thing. What exactly is that? So carbon spectral lines are very, very, very fine, I'd say. They're rare, like in that sense, hopefully you understand what I mean when I use those adjectives. So basically just very difficult to see in the universe, and we suspect that the matter in the universe that tends to absorb carbon, is usually cold gas from the early universe. So we look to quasars for neutral carbon absorbers. The tricky part about that is that we receive large swaths of data from quasars, and it requires a lot of effort to sift through it and find the carbon absorption lines. So, lo and behold, AI has saved the day with this issue. So astrophysicists have designed a neural network that is, developing through machine learning, and it's getting better and better able to detect carbon absorption lines in these huge swaths of data. And I should mention something that was brought up in the article itself. Quote, by stacking the spectra of numerous neutral carbon absorbers, the team significantly enhanced the ability to detect the abundance of various elements and directly measured metal loss in gas caused by dust. The results indicated that these early galaxies containing neutral carbon hopefully I said that, because I'm getting the word mixed up with observer. It's really bad. Sorry about that. Where were we? The results indicated that these early galaxies containing neutral carbon absorber probes have undergone rapid physical and chemical evolution when the universe was only about 3 billion years old, and the current age of the universe obviously being 13.8 billion. So what's nice now that we've gotten AI to do this for us is that the data that we're looking through here, it works very well with the findings that James Webb Space Telescope has. James Webb Space Telescope, it's got previous findings of diamond-like carbon dust in early galaxy spectra, and it's found rapid galaxy evolution. So as I just discussed with the quote here, those two go together. And so, yeah, AI might complement James Webb's findings very nicely. So there you go, more positive news for AI. Now, the third story. Speaking of early galaxies, we have some new findings on their evolution that doesn't need to wait for AI, and it also has to do with James Webb Space Telescope. So, James Webb, it's been peering as far back into the early universe as it can, and it's been doing that for a while, and it's found yet another thing. Very cool thing. It's caught early galaxies in the era of reionization feeding on clouds of cold, opaque, neutral hydrogen. Now, on the surface, that doesn't sound very cool, and you might not understand why that's significant, but obviously I'm here to explain that to you. So, give me just a minute. Let's go through the details here, though. Finish up with those before we get into the explanation. So, James Webb Space Telescope was observing 3 early galaxies in particular, and they were anywhere from 400 million to 600 million years old, after the Big Bang. So that does put it in the era of reionization. And if you're confused about the era of reionization, it follows the epoch of recombination, which we talked about in the last episode. I'm not going to give a super in-depth explanation to that. You can go and watch the last episode for that, but I will mention the key points here. When we talked about the epoch of recombination, we mentioned the cooling off of the universe from its high energy plasma state. So what the era of reionization is, it's kind of like the universe catching second wind. It's the cold neutral gas from the previous epoch becoming like more high energy again. So cold neutral gas in the epoch of recombination, it like settles down to a stable energy state, but in the era of reionization, it kind of kicks back up again and things begin to ionize. So why does that make sense? Why are we going from super high energy to low energy to high energy again? Like why won't it want to stay at a stable energy state? Well, it kind of brings us back to another point that I brought up in the last episode, is that matter tended to like concentrate in high energy places, which helped create the big ring, but that's besides the point. What is sort of helpful with that piece of information here is that because matter concentrated, it also kind of contracted. It might be because of gravity, it might not. I don't know. The article did not specify this, but my suspicion is that gravity would cause a contraction of this matter as well as it's concentrated. And so because it contracted in whatever way it did, it increases the energy of the matter to a point that it's possible for neutral atoms to become ionized again. And so that's why we would go from a stable energy state to a higher energy state. And so here's where our article has a say on this matter and why, the James Webb Space Telescope findings are really important here. Our theory about the formation of galaxies in the early universe was that these galaxies were formed from protogalactic halos pulling in neutral hydrogen gas, and a protogalactic halo being the center of a soon-to-be galaxy, but really just a cloud of gas. Astronomers now believe that, after we've looked at these 3 galaxies that have been feeding on cold neutral hydrogen gas, they believe that the James Webb Space Telescope data, it supports this theory that we already have about the formation of galaxies we see. And yeah, so astronomers believe this is the theory. This is the one. And according to a co-author, quote, "The gas must be very widespread and cover a very large fraction of the galaxy. This suggests that we are seeing the assembly of neutral hydrogen gas into galaxies. That gas will go on to cool, clump, and form new stars. The fact that we are seeing large gas reservoirs also suggests that these galaxies have not had enough time to form most of their stars yet." So the galaxies we've observed with James Webb are exactly the right moment that we want to be observing them. It's like just before a galaxy has been created or begins forming. And we see that it's taking in a lot of neutral hydrogen gas in that phase. So it gives us a lot of reason to believe that neutral cold hydrogen gas and its contraction is the primary and key component of galaxy formation. So that's what astronomers are saying. And that's the significance of galaxies feeding on cold gas. It confirms these predictions that we have had for a while. But I want to bring up an interesting point that'll lead us to a bit of a bigger picture idea here. A very, very long time ago, in season 1, I made an episode about quasars, an important component of the early universe. In fact, we just mentioned it with the AI stuff and sort of the neutral carbon absorption, right? But let me go back to what I was saying about the season 1 stuff. So in the episode about quasars in season 1, I mentioned the simulation of the early universe, which revealed that quasars formed from the collision and collapse of cold gas streams. That begs a really, really important question. Which model of galaxy formation is more favorable and might be more common in the universe? Is it collapsing cold streams of gas that turn into active galactic nuclei and black holes? Or is it contracting cold gas that creates protogalaxies? Which came first, black holes or galaxies? Now, that is a question that I will leave up to the viewer because I've talked about it quite a lot and I've brought up both sides of the argument across the course of this podcast, but the question still remains, and it's up to interpretation for now. So that's all I have for you today in this episode. Hopefully you all enjoyed what I've talked about here, considering that you've made it all the way to the end. You probably have. If that is the case, then make sure to subscribe to me on YouTube if you are listening on YouTube, and if you're listening on Spotify, I'll make sure to follow me there. And yeah, until the next episode, I will see you all later. Peace.